Okay, good morning, everyone. This is the last lecture for this subject, and once we finish this, the remaining of the classes that will be dedicated to exam preparation. So we have plenty of um, preparation examples to work on. Also, if you want to bring something to be discussed or solved in the class, please bring them in. And before I start, any question from before? All good? Okay, so today lecture we conclude the topic of internal stresses. So what happens internally inside the structure is important because that is invisible, and a good way of measuring the risk of the crack growth is by measuring not the internal forces but internal stresses. Internal forces, yes, they are a measure of force, but it is not force that causes the structure to collapse. This is a combination of force, geometry, and material, which causes the material to collapse. For that reason, we have to measure what is called a stress. And in beam structures, two types of stresses develop inside the beam. One is the normal stress. The second is the shearing stress. So normal stress, shear stress are not unique. They are not specific to the bending. So any kind of loading that would result either in shearing stress or tensile or um, normal stress. Okay, but for the, as far as the exam is concerned, you want to know the concepts of the normal stress, shear stress. Normal stress is when your force is perpendicular to the area. So it means a stress only makes sense if you are talking about the surface, if you are making about a section. So if you make the section at a different angle, stresses would be different. All right. So that's not only the function of force area, but also the orientation of the area. So the orientation of the area, you could make it such that the area is perpendicular to the force. That becomes normal stress. So you can think of the stress something at a point, depending how do you evaluate it, what are your coordinate system, the stresses would be different. And then when there is a beam subjected to the bending, we already discussed that due to the bending moment, there will be a normal stress. Normal stress is comparable to when you try to pull something or push something axially. But what is shearing stress? How on earth shearing stress develops inside a beam? So to make this easier to visualize, imagine that a beam is composed of a number of layers. So you can think of a book, just you have a notepad in front of you, try to bend it, and what happens is the pages start to slide tangentially, right? So how could you prevent this from sliding? If you would have had some glues between the layers, when you try to bend, the glue were subjected to the shearing stress. Can you imagine? Because the sliding force is tangent to the interface between that plate and that plate, this paper. So that causes a shearing stress. Okay, so this is not the reality. The reality is, if that's a wooden beam, all layers are glued together by wood. So this is really the wood which is enduring the shearing stress. If that was made of any material, when you try to bend, those imaginary, those virtual layers would tend to slide, and then what stops them is the material stops them to slide. Okay, so you can think of these stresses developing between the layers. And then when I say layers, it means in the transverse direction, you see a difference. Now, I want you to visualize there is no layer at the top. I mean, imagine this is the first layer. Before the first layer, there is no layer. So does it justify that the top layer does not develop any shearing stress? Because there is no layer next to it. When you try to bend the top layer, that's the first layer, no layer before that. So zero shearing stress between the no layer and the first layer. So that is the zero shearing stress at the top. Also, the very same thing can be justified at the bottom. Bottom is the last layer. So when you bring an imaginary layer after that, there is zero. So you could think that this is not quite the same as normal stress due to the bending. Because when I bend, the maximum normal stress develops either at the top or at the bottom, depending which one is farther from the neutral plane. But here, you expect the maximum to be somewhere right in the middle. All right, I told you the story. The rest is to find mathematical relationship between them and find them why this is so. But you don't need the mathematical relationship. Even by just visualizing that this is rule of thumb, you can visualize, and then believe me that that's in many cases when you are evaluating a system, your common sense would help you to just make the right judgment. All right, so that is called transverse stress. Transverse stress, we are talking about the transverse direction, and transverse direction generally we show that by parallel to y coordinate axis. So if this is my beam, so axially that would be the axial direction, we call this x, and generally speaking that x-axis we locate that on the neutral plane. We don't put it at the bottom, we don't put it at the top. So if that's a rectangular cross section, I have to put my x-axis right in the middle. If that's a T-section, you have to find the centroid of that area and put your x-axis along there. What about the y-axis? Y-axis is always perpendicular to that one. So this is y-axis. We call this transverse. So remember I told you that after the bending, there are two stresses developed here. Normal stresses, that was the flexural formula. We discussed that last week. It not only depends on x, also depends on y. So in another word, yesterday we were trying to find x star, y star. What are x star, y star? X star, y star is the location at which the normal stress is maximum. So because this formula is my divided by I, it makes sense this is maximum when your bending moment is maximum. All right, so you are searching for a position where the bending moment is maximum. That position axially, this is your x star. And then the second question is, what is y star? So at the very same, imagine this is my x star. This is my x star. And the next question is, okay, I know that this normal stress is not uniform. It changes from top to the bottom. And then remember, for normal stress, it is always maximum either at the top or at the bottom, depending which one is farther from the neutral plane. Why is that? Because y is the distance of the point from the neutral plane, and the farther point is either the top or bottom one. So we don't have any problem for that. Hopefully everyone, at least from concept point of view, you know what we are doing. We are looking for x star, y star. How do you find x star? You plot the bending moment diagram. By looking at it, you find the maximum is there. But how do you find y star? This is a section I mean, you have to imagine this is the section. Okay, I find the neutral plane, and then this is a judgment. Is this one larger or this one larger? Whichever is larger, that would be the y star. Okay, now the very same story for shear. So when you bend the beam, shearing stress would develop here. And there will be an equation very similar to the flexural formula, which tells us how shearing stress is not only function of x, also function of y. So let's call this x double star and y double star. Why did I choose them differently? Because wherever the normal stress is maximum is not where the shearing stress is maximum. There are two. At the end of the day, once you have both values, you have to compare which one is larger. The one which is larger is a more serious threat for crack growth. All right. So this, for now, you just know that shearing stress is not only function of x, also is function of y. And then I tell you that here, this is internal stress, internal force. What is the mate for that internal? This is shearing force. You know, we, for every beam, two type of graph we plot. One is shear force diagram, x. The second one is bending moment diagram. So from bending moment, I go and calculate this one. From shear force, I go and calculate that one. All right, let's get into some mathematics or visualization. Here, this is an extremely important thing to understand. So imagine this is a wooden plank, and somehow I managed to cut a cube from an arbitrary point. So I'm removing a cube from here, and enlarging that cube is being shown here. So you can imagine that this direction is axial direction. Axial direction, also we call this longitudinal direction. Longitudinal, axial, okay, both of them the same. And then this plane, that's the y direction, I call this transverse direction. So please listen carefully. The shearing stress on two sides here, I mean a transverse side and, sorry, transverse side here and longitudinal side here. Shearing stress develops on both of them, and you know what? Both of them are equal. So in another word, if I want to find this one, which is difficult to find, I can simply find this one, and for, as a matter of fact, I know that this is equal to that. These are like pairs. So think of the couple. Couple is only defined when you have two forces of equal magnitude in different direction. So think of this as a couple. So you won't have shearing stress here without having shearing stress over there. Otherwise, the shape won't deform. I mean, if I show you the before deformation, that's the rectangle. Then when you apply this one, it turns into a deformed shape, right? So for that to happen, you need these forces to be in couple of equal magnitude. So what I'm saying is this shearing stress is equal to this shearing stress, and therefore the transverse shear stress is equal to that of the longitudinal one. All right, so the derivation we present here, these are for the transverse, for the transverse, but that also applies to the longitudinal one. Okay, and then just one more thing. Look at the size of these arrows. The arrows start from 0 size, they gradually become larger, and they become maximum somewhere before they become smaller, and then shrink to 0. So that, remember, despite all the mathematical derivation, that is the thing you would take with you from here. During the bending, the shear stress is 0 at the surface, 0 at the bottom surface, somewhere maximum in the middle. And I tell you what, that somewhere is, generally speaking, is the neutral plane. Okay, so when you stretch these apex, these corners, the shape deform like so. And therefore the stress which develops on the top surface and side surface, they are equal, longitudinal. And then here, this has been illustrated. So now, we want to derive the shear formula. For doing that, I choose a very simple beam. That simple beam is simply supported. It's being loaded right in the middle. And then I decide to make an arbitrary section of AA. If I make section AA, that's the cross section. It's a rectangular one. And we want to derive the shear formula here. So what do I do is, first I need to plot the shear force diagram. It's not difficult to do the shear force diagram here. That is my x-axis, and this is the shear force diagram. It starts with P by 2, the reaction at here, P by 2, and then it doesn't change until the middle. There are two zones, zone number 1, zone number 2, right? Here, right in the middle, you have a shear discontinuity. I told you that the shear force diagram, bending moment diagram are always continuous unless you have a point shear that makes the shear force discontinuous, unless you have a point couple that makes the bending moment diagram discontinuous. But other than that, the shear force diagram, bending moment diagram are always continuous. All right, so this is, with this very simple, we know that the maximum shear everywhere is maximum, right? If you ignore the sign P by 2 minus P by 2, everywhere the shear is maximum and the magnitude of the maximum shear is P by 2. All right. If I plot the bending moment is maximum where the shear force becomes 0, right in the middle. And in between, it increases linearly, decreases linearly. All right. So now let me choose a tiny slice which is measured x from the left. So you see that pink coupon? That is a slice. I made a slice of this one. The thickness of the slice is delta x. Okay, delta x. And how far this coupon is from the left? That is x from the left. All right. So think of the internal stresses. Internal stresses in this side and internal stresses in that side. They are not the same. Because I told you that the normal stress is a function of x. Because the bending moment changes. When you are here, the bending moment is that. When you are there, the bending moment is that. They are not equal. So if I try to show that internal stress on the left and right hand side of my coupon, unfortunately, those variations are not uniform. They are maximum at the top, minimum at the bottom, 0 at the thing. So you end up with two different distributions at the right and left. So the distributions are like so. That is my coupon. So left hand side, I have the normal stress due to the M. Right hand side, I have this due to the M plus dm, because M has changed. M has changed between left and right. So how can I solve? This is a free body diagram. That free body diagram has a distributed force. So like usual, how did we do that? We replaced the distributed load with the point load and the line of action and solve the free body diagram. So I make the long story short for you. You won't be asked about the derivation. That is all you need to remember. If I solve that free body diagram, the outcome becomes a very interesting formula. The outcome of solving that free body diagram, eventually you end up with something like this. The shearing stress is equal to that. All right. So let me simplify. Let me make this easier for you that equation because that equation is very scary. We just want to make this simple, understandable, and practical. So how this can be done? Let me bring that formula into a scrap page here so we can work it out together. Okay, according to this derivation, my shearing stress, when I say shearing stress, it doesn't matter if that's transverse or longitudinal, both of them are equal. My shearing stress is equal to 1 over I, and B, I tell you what B is, and then multiply by dm over dx. And finally, an integral which is y multiplied by dA. And this is over the area. All right. I, that is the second moment of inertia. B is, okay, I'm developing the shear stress, for example, at a certain point. I have to travel from here to here. That is B. So if that was a section like this one, and I'm developing shear stress at this plane, remember those layers, the papers are trying to slide. If I'm evaluating the shear stress here, my B, I have to travel from here to here. That is B. If I'm evaluating that here, the sliding layers, that's the length of the sliding layers in the third dimension, in the third, not longitudinal, not transverse, but the normal to that. So this is B. So I know what B is. We go through some good examples to make sure everyone can identify what is B, what is I. And then this one, does this sound a bell? Do you remember seeing that one anywhere? When you did the diagrams, method of equation, which equation was using the derivative of m over x? So let me remind you, when we did the method of equation, the distributed force was the derivative of the shear force by x, and shearing force was derivative of the bending moment by x. That is back 2 weeks ago when we did the method of equation. So from here, I remember this is, I know this guy, that is V. Okay, so if I want to simplify that equation one more step, shearing stress becomes V divided by I B, and that multiplied by an integral of y dA over the area. Okay, y times dA integral, what is that? So we call this Q. We call this Q. That is a geometrical parameter. I told you that the stress is the function of geometry, load, and material. All right. So this is a geometrical parameter. I is a geometrical parameter. B is a geometrical parameter. V is a parameter of force. So the shear stress, eventually, that becomes the shear stress of x and y. That is V multiplied by Q divided by IB. That's a very short equation. So for these, the most difficult chapters for final exam, that's the bending stresses. Two stresses, normal stress, you find this by the flexural formula. Shearing stress, that's the equation. So remember this equation, just think of them as a recipe, and we go through lots of examples, making sure everyone can do this. All right, before we go any further, let me remind you of when you wanted to find the y bar. Do you remember that was integral of y dA divided by A. Remember that? Okay, if I manipulate that equation here, so I mean, in another word, you might remember this as the summation of y1 a1 plus y2 a2 plus and a1 plus a2. Okay, that was another way of this. So this is the same thing, but by manipulating that, I get that the numerator is q, that is q, and I will have y bar multiplied by a is equal to integral of y dA over area. So in another word, you don't have to worry about solving an integral. It would be much easier if you substitute that q value by y multiplied by a. All right, so let's do some examples. I want everyone being confident to calculate q. All right, in doing that, I'll give you a numerical example. So let's have a rectangle. This rectangle is 20 millimeter in width and 100 millimeter in height. Okay, and that's a neutral plane. Neutral plane is right in the middle, 50. So let me put a number of points here. Point A, point B, point C, point D, and point E. Okay, let me, I mean, we are looking for QA, QB, QC, QD, and QE. All right. So how do we do that? To calculate Q, you need a very sharp knife. So this is my knife. And this is like a samurai knife. You just pass it from here to there. And then you manage to split the section into two pieces, upper pieces, lower pieces. Here, the upper pieces is 0. If I pass that sword from here to here, then I will have an upper piece, lower piece. Okay. To calculate Q, you are welcome to use either the upper piece or lower piece. Both of them give you the same number, but one of them is much easier. One of them is much easier. You'll be smart to choose the one which is easier. So maybe I start with QB and then we go to QA. All right. So if I use that sharp knife and split that in two pieces, that becomes number 1, and anything here that becomes number 2. So that is 100, this is 50, this is 25. All right. With that dimension, are you able to calculate the area of the A, area of 1, or area of 2? No, right? And are you able to find the distance of each area from the neutral plane? So this section A, where is its centroid? The centroid is right here. So that centroid measured from here, I call this y bar 1. Alternatively, I could have calculated the centroid of the lower piece. The centroid of lower piece is here. And the distance of that to the neutral planes, I call this y bar 2. So I'm saying that QB is either A1 multiplied by y bar 1, or that is equal to area 2 y bar 2. So let me summarize this for you. You've been given a section, and that sharp knife is where you want to split that in two pieces. Why do you want to split it in two pieces? Because you want to measure how these two pieces are going to slide. When I say a slide is the shearing stress. You want to calculate the shearing stress. So if I want to find shearing stress, I have to pretend that I'm splitting that right in the middle, and then I'm measuring how these upper piece and lower piece are sliding. Make sense? So finding Q is the most difficult part of the shear stress calculation. I want everyone to be confident and understand why we are doing this. If I want to find the shear stress at point D, I need to split that virtually into two pieces, upper piece, lower piece. And then for each piece, you find the area, and you measure the centroid of that area from the neutral plane. That is Y bar. The product of Y bar by area, remember that's the equation we derived, right? So we said Q is Y bar multiplied by A. So if I decide to split that through A, well, you have to calculate two things. First is the area of the upper piece, lower piece, and multiply that by Y bar. So the area of the upper piece is 0. So multiply that by whatever the Y bar is. So I know that the Q at A is equal to 0. Okay, so this can be done in two pieces, two formulas. That is A1 Y bar 1, A2 Y bar 2. So it's easier to calculate this from the upper piece. The area is 0. If you try to do the lower one, you find out that the A is not 0, but what is Y2 for the lower piece? Y2 is the centroid of the piece measured from the neutral plane. It is coincide. So the distance between them is 0. So the right one is 0 times something, and the left one is something times 0. All right? But it would be smarter if you pick the upper piece rather than the lower piece. Yeah, the last one. Yeah. Why? Yes. Good question. So let's follow that steps, Ahmad. So where is my point A? My point A is here, right? So if I split that in two pieces, the upper piece area is 0. And what is the Y bar? The centroid of that 0 measured from the center. So this is 100, that's 50, right? So that is from here to here, that is equal to 50. All right? So Q1 is 0 times 50, that is 0. Or let me choose the lower piece. The lower piece, what is the area of the lower piece? The area of the lower piece is 100 times 20. Yeah. And what is the Y bar 2? So the centroid of the lower piece is here. How far the centroid is from the neutral plane? 0, right? So here, that is 0. So that is 200 times 0, which is 0. Here is 0 times 50 is 0. But the upper one is easier. The first option is easier because, yeah. All right, let's go back to the same problem. Now, can I get everyone trying to calculate Q of B numerically? Can you calculate Q of B numerically? So I make this easy for you. So QB. So I split that in pieces. Okay, which part you want me to explain? Is that, can you follow what we did? I mean, when I say y1, this is y bar 1. That's the centroid of the segment measured from the neutral plane. All right, can we do the calculation for point C? Can we do the calculation for point C? Okay, let me do that for section C. Can I remove this? All right, we want to use the magical knife, and that magical knife would split the beam into two pieces. All right, so these are two equal pieces, A1, A2. So for this one, Y bar 1 and A1. For this one, Y bar 2 and A2. So A1 is just 1000, and the same here. What about Y bar 1? So this is the centroid of the upper piece, measured from here, that is equal to 25. And here, that's the same thing. This measures from here, that is also 25. And what is the product? The product is Q is, that is 25,000. All right, so do you remember the last number we calculated? Is this larger or smaller than that? Q, larger. So if we go and calculate that of the D, it becomes smaller. So why the shearing stress becomes maximum at the neutral plane? Because the Q for that is maximum. Everything else is the same. So for one given cross section, the shear force doesn't change. You look at the shear bending shear force diagram, that is only function of X. It doesn't depend on Y. So V is the same. Let me show you the formula. That is the formula we had. Look, shearing stress is the product of the V, Q, I, B. So the only thing which could change is either Q or B. So you might ask yourself how B might change. I show you how B might change. So that for a beam of composite cross section like this one, where is my neutral plane? So neutral plane is somewhere like here. Okay, then you choose your samurai knife to cut this from here, split it the upper piece and lower piece. How far your cutting tool would travel? It goes from here to there. So B over here, that is, for example, this is 100, and that is cut A. If I do cut B, so here B of A is equal to 100. If I split the beam in two pieces, lower upper, so from here to here, B of B is equal to only 20. All right, so in that formula, I said that this is not only function of X, but only function of Y. Both Q and D, they are function of Y. So depending what is the cross section, you can find out the maximum value. And then just tell you something. Look, if I just make the section here, B doesn't change, right? Immediately, if I move a little bit lower, B becomes smaller. So there is a discontinuity between B. B jumps from a large value at the top to a smaller value. So you expect to have a shearing stress discontinuity when you are near that point here. And that makes sense. In that section, suddenly at the top, the shearing stress is large because the area is small. When you go lower, the area becomes smaller, the shear stress becomes large. So if this is a very risky area, you might have crack growing here. That's a stress concentration. They call it a stress concentration. When suddenly the stress grows or becomes smaller, that's a stress concentration. That's where you might get this one to collapse. All right, so I think um, it's I get a feeling that everyone understands the concept, and if you understand the concepts, all done. What is left is just practice. We have to do this for different cross sections. I mean, um, in one of the things, uh, all right, so it's difficult to manufacture complex cross sections, right? You only find cross sections of standard lengths. Sometimes, if people want to innovate, they want to make something themselves, a cross section themselves, they might think of, look, I'm going to either weld or bolt together a number of different cross sections to make something like that. But this is a silly fabrication. Why? Because right here, I mean, I exaggerated the gap here. Right at here, at the top, the B is from here to here. Below is here. At that section, B becomes suddenly small. So if they wanted to fabricate something, it was much more reasonable to join this and get away with that variation. You know what I mean? Because that point where you have a smaller b, b goes to the denominator. The smaller the b, the larger the shearing stress. That means you want to avoid that. And yeah, these are some of the questions in your end of chapter book. I mean, we went through the concepts, but what remains is the numerical values. So, okay, one thing to remember, sometime that travel of the cutting tool is either called T or B. Both of them are the same. Different textbooks, they are using different notations. They're the same thing. So tau is the average shearing stress at the point. V is the shear force. Where do you get it? You get it from the shear force diagram. Q is first moment of area about the relevant axis. It's a very a strange word, but what it means is that's the product of y bar multiplied by a for either of the section, either the upper section or the lower section. I is the second moment of inertia. B or T is the width of the beam section at the location of determining the shearing stress. All right, so now we can do this for a simple beam which is simply supported. If you apply 2 kilonewton, that's a symmetric. You know that this load would be half at the reactions, and then you plot the shear force diagram. Everywhere is maximum. So the maximum value of the Q is, V is 1 kilonewton. All right. Then that is the cross section. So you know the maximum V. The maximum V is 1 kilonewton. So my formula for calculating the maximum shear, this is for shear in general, but generally speaking, you are looking for X double star, Y double star. These are where things are maximum. All right. So all X values are X star everywhere. That is this. But the question is, in the Y direction, can we do calculation either here, there, or here, or even in the middle? If you find the Q for these values and plug them into this equation, tau is equal to VQIT or IB. So to investigate which of these points develops the larger stress, all you have to do is you have to find Q at these points. And we already did that, right? So if you do them, because T doesn't change, I doesn't change, V doesn't change, that would be only a matter of Q. Next question. How does this vary? I mean, I know that this is maximum in the middle, 0. Is this going to change linear or quadratic or cubic? How does it change? It's not linear. In terms of the normal stress, it was linear. But here, that's going to be quadratic. Why this is quadratic? Give you why. What is Q? Q is Y bar multiplied by A, right? Already Y is here. What about A? A is equal to Y multiplied by B. So that is BY squared, something like that. So it makes sense that Q changes quadratically with Y. If that changes quadratically with Y, you expect to have something like this one. That is my shearing stress. So here, that is 0. Here is maximum. And in between, you have a quadratic change. And then again, to go back to 0, it quadratically goes back to 0. You don't have to drive it. This is just a simple justification why this is quadratic, all right? All right, so let's do this for some more complex cross section. That was a simple cross section. So this is a crazy way. I mean, with that simple beam, what we did here, we made a slice, we developed the free body diagram, solved the free body diagram, and calculated the shear stress. And also the very same problem, we solved that using the formula, both of them giving the same number. So that's just to give you a peace of mind, but you don't need that. All right, the next thing is let's, for the remaining of the class, we're trying to solve this problem. All right, let's have some 10 minutes to find out the reactions and to plot the shear force diagram. From shear force diagram, we try to find the maximum shearing stress. 10 minutes start now. Okay. Please find the reaction forces and the shear force diagram.
I am not related to Johnny Sins. Like on my Facebook, they're comparing my Facebook photo to John's tits. This is bullying, guys.
That's what I've been doing for that.
Being cold, good answer. Very least, I want to pass the data thing. I can't do it yet.
What data?
The data.
Oh, the digital system.
Digital system. Digital data system.
Yeah. Why don't you do it again?
They're not running it again.
Oh,
It's
really?
the last one.
Sure.
Electronics, they're only doing it the first semester as well. So,
What are they replacing it with? Something different.
yeah. So, I just want to pass that. I've already agreed on this one.
It'd be so much harder than that. You got like Shaheen or something. You got the bald guy, yeah?
Yes.
Short? Yeah, he's not it is fulfilled.
No, if I pass, it's more than 50, but which I'm hoping for, considering I'm pretty sure all these videos will robot work.
Yeah,
so much harder. That's really probably the hardest.
Dude, the arm one's so easy.
It is.
You just like program open and close.
Yeah, and then show BPM. Yeah. Oh, I wish we did.
Help me then.
I can't help.
Yeah, you can.
Yeah.
Yeah.
Who say you cannot help?
I didn't do the code. My teammate did it. I
You
thought
said it's easy, just help me then.
I thought the robot, my teammate did the code. So,
It's so annoying. With the robot, we're not given the actual size of the arena, so I can't actually test it.
oh, it's better so it's okay.
Is it actually? Lovely. That's really painful.
I don't think we programmed the size of it. We didn't have it. We just did like less than that. Until it found the part and then decided it was red or blue. It was blue.
Then I have to put it in the no, with red. I have to put it in the line.
And
I
I
put
put
it
it
in
yeah.
the.
Ours was cool. I mean, it didn't work very well.
But as long as it works.
Yeah, it moved around and shit. So.
Oh, I thought you
Grab
could.
some pucks.
I
Then around now.
Oh, okay.
Yeah. I wish we did that.
I would look at it. And link the whole
You mean the undergroup of his course is broad.
The only thing
He
is
does.
body my hand.
Oh,
Body.
Smart.
did you have to get an add-on to the data acquisition for that?
I think so.
Yeah. You never told us that. It
was
just
I
plugged it
did.
in and it didn't work. And I found an example online and it still wasn't working. And the same error. Please download this. Like, please, it may not work because you do not have this. Like it wasn't definitive.
Yeah.
It was like, I clicked on it. And it took me to like some random site, which took me to the MATLAB website to download it. So weird.
Probably like something.
Well, it was fine if you got Bernie to teach you how to do it instead of study. Then you go to lectures, right? What day lecture? The data.
Thank you very much. Do you go to any lectures on Monday then? Which one?
He's
the only one.
Yeah, he's the only one that works.
The only one that attend every class. Only one.
That's why I asked him.
Well, he lives here.
Yeah.
Easy for him.
But for online, you don't need to meet here.
Yeah.
Maybe for online, everyone attend. For the
Yeah.
You know,
He only made a point yesterday.
even when I attend the class, I thought I just left.
What the?
Monday's fun.
Besides,
Precisely! That's why I'm thinking. I love every day, suddenly.
Oh, yeah.
Used to be the best day. I like how he can come back and no one's done it. I slept until 3. Yeah. Precisely, like, we don't 73 hours straight, yeah. No. I do some of them, but not, definitely not plus any of those. Oh no. And then he doesn't teach you in class, and so you just walked. How does Sunny still working here when you're arguing fired? Who's fired? Yeah, I mean, she was not good, but she was better. She's definitely the worst. I'm actually friends. The husband and wife, they're not the one. But I miss Prince. Yeah. I never thought I would say that. I never thought I would say that.
For the side, yeah.
If he explains,
It's not the side,
yeah.
I thought Prince was good.
Are you seeing catching the train too often?
feel special. You appreciate you being active while using it together. Just had to do it our way.
Yeah. I don't have to find somebody so
That-
to do it, but
Do it.
do it. You're in a car.
Can I see?
You good at soccer?
You do soccer.
If you go, they haven't broke his ankle.
Very sure.
You just hit everyone.
Kick everyone's
Yeah, he's go there, he didn't play soccer, he played football. The one that you rest of the elbow.
25 each. Yeah. We're going to your place and smash.
That's how you go.
And this is just a little bit of test and get a host.
Yeah, we'll make it right. We'll fit. We'll squeeze on top. We'll add our shear force. We'll go on top. We'll have a lot of shear force. We'll be stacked up higher.
Is that like on the side?
Just take your weight outside.
Exactly. We'll disassemble it for you and put it together. Don't worry.
Or just have all take outside.
Hey, ready?
Yep.
All right, what are the steps? Let's summarize the steps first. Here, the question is, I want to find the maximum stress inside a beam. This is just a simple beam. So what do I need is to realize that this maximum shearing stress is not the only stress. Also, there is a normal stress. So eventually, you not only have to find the maximum shearing stress, you have to find the maximum bending stress and compare which one is larger. Having said that, this exercise is just for finding the maximum shear stress. So the first step is, Natasha is going to tell us what is the first step. To find the reactions? Yes? Okay. Good answer. Finding the shear stress. And, well, not only the shear, the reactions, the next step is to find the shear force diagram. Why do we do shear force diagram? Because that in one snapshot, it shows you the maximum number. I mean, if you can just find the maximum with other means, I can't imagine any other way of telling you what the maximum shear force is. But once I know the maximum shear stress, how do I know it? I grab this from the shear diagram. So by looking at this, who can tell me what is the maximum value, the shear force? 4.8. So it means the most critical points of this beam from shear stress development is right at the left reaction point. So now I have this one. What other question should I answer? So to answer that question, I need to remind myself of the shear formula, which is the shearing stress is not only the function of V, it's also function of Q, it's function of I, it's function of T. All right, so finding I for this section is not complex. I mean, what are the steps? The steps are, first, this is a composite shape. You have to find out the neutral plane location. All right, so I split that in two pieces, A2, A1, and then Y bar is simply Y bar 1, A1 plus Y bar 2, A2 divided by A1 plus A2. That is, you locate the position of the neutral plane. Why? Because when you are calculating Q, every calculation is using that reference. You need that reference. All right. So we know how to calculate Q. If I make a section here, there would be a zero area at the top and something at the bottom. So at that top surface, the Q is zero. So it tells me the shear stress can't be maximum there. It is zero over there. So the next point is, what about here? If I split that here, I would have a block here and another composite block at the bottom. So it would be crazy if I decide to calculate that from the below. I know that this should give me eventually the same answer as that of the top. So if I want to find Q at this section, a reasonable option is to find that area and to find the centroid of that area and multiply them together. That is Q for the upper. Don't go for the lower part. That gives you the same answer, but it's very, very complex. Now, the next thing is, if I do that at this section, if I do this at this section, that's going to be tricky. Why this is tricky? Why this is tricky? Think of discontinuity. Do you see any discontinuity there? For what? For the one at the denominator, this one, right? So a little bit at the top, what is T? A little bit at the top, T is equal to 20, but a little bit down, what is T? So think of this as your sword, which is going to travel. For here, you are making the block sliding on a horizontal block. But if you slide this, for example, here, then you have a large sliding surface, right? Suddenly there is a jump in that thickness. So I expect to have some jump into the shearing stress right in vicinity of that point. Because there would be a jump for T. Also, Q, maybe Q is not jumpy. You get the same Q before and after, but that in the denominator would make it. And which one is more critical, the one at the top or the one at the bottom? Which one is more developing larger stress? The one at the top, because that has a smaller t in the denominator, makes the stress larger. Make sense? All right. Now I show you the plot. The plot for that is variation of the shear stress. So at the top is zero, at the bottom is zero, because once you cut, the upper piece has a zero area. When you cut it at the bottom, the area is not zero, but the y bar becomes zero for the lower part. So shear stress becomes zero at the top, at the bottom. And now if I do that at the mid plane, yes, I can do the calculation of Q, and my shear stress over here would be 4.4 megapascal. If I do this right at this continuity point, I'm going to get one number from below and one number based on the above. So that discontinuity you see here, if you just use quadratic curve to connect them, so one quadratic to connect this one to here, one quadratic to connect this to here, and then there is a discontinuity jump, and one quadratic to connect this from here to there. That is the variation of the shear stress over that cross section. I mean, you're going to have the maximum right at the neutral plane. So remember, the shear stress is always maximum at the neutral plane. Is zero at the top, zero at the bottom, maximum at the neutral plane. So that is bringing the lecture to its end. And my congratulations to everyone. You are a certified structural engineer. And yeah, let's see that. Let's see that. I don't want to jump in conclusion, but yeah, just anyone missed the third track except you? I send you the data. Have you got the data?
I didn't get an email, no. I'll double check now.
That was last week, same time. We emailed you. I think someone reminded me of you. You missed it. Have you got the data?
No. I do, yes.
Would you forward that for Darcy also? Daniel, anyone is in contact with Daniel? No. All right, we send him data.
When's it due, sir?
Due.
That's like 2 weeks.
All right, you have to do the reading. And then I tried today to upload the recording of the session. Maybe just by watching the recorded session, that gives you some hint. All right. Otherwise, you have to read the document. And then tomorrow, if you have question for the instruction, bring it to me. I'm happy to explain this more for you. Okay.